recording. Okay, so I'm honored to present Professor Giora Rytwo from Tel Chai College and Migal Galilei Research Institute. Professor Rytwo research focuses on environmental research, chemistry, physical, and water pollution. His research attracted over $3 million of funding over the last 20 years, and among them is the REVA project in aquatic pollutants, AeroNet. He has over 100 scientific publications in books and journals, and he delivered more than 30 presentations in international conferences. He's also recognized a leader in industrial innovation. He's a senior inventor of water technology cleantech company and the sole inventor of a few patents in the field of methods for pretreatment of wastewater and recreational water with nanocomposites. And today, Professor Rytwo will present on clay-polymer nanocomposites for water clarification and suspended solid removal. So in the end of the lecture, we will have 5 till 10 minutes for questions, and you may write them on the chat. So Giora, the floor is yours.
Thank you, Neta. Again, I will deal, as Neta mentioned, with the clay polymer nanocomposites for water clarification. If I can prepare a kind of PDF file with the slides, if somebody wants it afterwards, you can here in the brochure, if you click read more, you can get to my email. If you send me an email asking for the PDF of the slides, I have no problem in sending it. Anyway, as Neta mentioned, the lecture is recorded, indeed, and the link will be sent to you afterwards. There are several patents on that issue. Since I think the first one was about in 2012, but I cannot deal with turbidity and suspended solids removal without starting with saying a few words about what is turbidity, where are suspended solids, and how did we get to the idea of kind of let's say a special approach to in trying to remove them from water. This lecture is also part of an e-course organized by the Rio project, as Neta mentioned, which is an AeroNet project with researchers from Finland, Denmark, Israel, and South Africa. As Neta mentioned, I deal mostly with environmental physical chemistry. In the last years, a lot of issues that are related to water and wastewater treatment, including coagulation processes and AOP, advanced oxidative processes of contaminants of concern. But we also deal with slow release of pesticides, for example, aiming and minimizing environmental hazard, and in general with interactions between small particles, in most cases play mineral, but not only with organic compounds, and also with modeling of absorption and kinetic processes, and some micrometeorology issues that are related with the CO2, water vapor, and energy fluxes. The lecture today will start with trying to making a reminder of about what is suspended solids, what is turbidity, are the same, and if not, what is the difference. Of course, that we will need to mention colloids and what is a colloidal charge and zeta potential, and what are the usual treatments for suspended solids and turbidity. Of course, that I will focus afterwards in what we developed, specific and very efficient, relatively compared with other approaches, method for the clarification and removal of suspended solids that is based on polymers, charged polymers, and clay minerals that are bound together to what it's usually called the nanocomposite, because it has also a mineral part and an organic part that can be adapted to the specific effluents that we want to deal with. So, as we all know, in such a lecture, water is very important for everything, and the freshwater water sources are limited. And if we make water dirty, then it's very difficult to clean it afterwards. And any approach to try to increase the amount of available water includes either taking the water and transferring it from a river or a lake to other place, taking the water from the sea or from saline sources and try to remove the salt from it, or purification of effluents, taking the water that we already used it once and try to use it together. It doesn't matter which approach you are taking from the three of those. In most cases, you will need at the beginning to remove turbidity and suspended particles that are there, because they will be a problem otherwise to the following treatments that are coming afterwards. So when we talk about suspended solids, what do we mean? Water can contain silt, particulate material that's coming from the soil or from the construction runoff, or from or algae that's coming from the from nutrients. All those particles together are contribute to what we call turbidity and total suspended solids. That means they make the water turbid, and on the other hand, they also contribute to solids that we don't want them to be in the water. In natural water, most of the TSS are inorganic minerals and bacteria, and desalination plants, TSS may clog reverse osmosis membranes, and in any treatment plant, even if it's for agricultural water, those particles can clog the filters, as you can see here. Of course, that in rivers, you can see the turbidity of the water and the particles that are here in comparison with the water with considerably less amount of suspended solids. The amount of suspended solids can range from 10 or even 5 milligrams per liter in very clean streams to more than 50 grams per liter in heavily loaded effluents, like, for example, in olive mill wastewater. For example, if we take a look at a few sources, here we have fish ponds or washing machine effluents, or a recreational lake, or a garage water, or hen houses, or a stream, or a spring, and we can see that the TSS may be in the range that I mentioned before, between about 10 milligrams per liter if the water is relatively clean from natural source, to several thousands if the water is very dirty. That means if it has a lot of particles in it. Let's set a few limits in order to put the numbers into a perspective. In Israel, at least, the outlet standard for water treatment plants is 10 milligrams per liter. That means that all those samples are above, cannot be released by the wastewater treatment plant. And the inflow in Israel, it's I wrote here the wrong number. It's not 10 milligrams per liter, it's 400 milligrams per liter. That's the maximum that you can put inside. Otherwise, you are usually fined by the regulator. That means that it's not forbidden, but you need to pay more in order to get your water cleaned. That means that we have particles, and those particles clog the system, and in order to remove them, we need to do something. And those particles are usually very small, are what we call colloids. Colloid, in general, is a mixture of of two phases. That means it can be solids in water, like in our case, and it can be liquid in air, like in fog or a cloud. We have tiny particles of liquid that are dispersed in the air, in the atmosphere, in the gas, and we have that colloidal particles, in order to remain more or less stable, are in a range of size of 1 nanometer to 1 micron. This is usually the range that it's known as the colloidal range, and some of the colloids are translucent because what is known as Tyndall effect. Tyndall effect is caused by scattering light by the particles, and in order to scatter the light, the particles should be on the more or less on the size of the visible wavelength of light. And that means about 200, 300, 800 nanometers. But even if they are smaller or slightly larger, they will disperse light. And this is what we know as Tyndall effect. You can see here the turbidity. And a stable colloid suspension is the use stable. The term stable is used in order to define a suspension that does not separate alone, like fog or a cloud or turbid water. So we spoke about suspended solids. Let's say a few words about turbidity, because as we see, those are related. Turbidity is the cloudiness that we see in a fluid caused by particles that are usually in the range of colloids. That means 1 to 1,000 nanometers. And those particles interact with light and make the water turbid, like you can see here in those examples. And those particles can be of mineral origin, like clay minerals or clay-sized particles, or organic matter like pollen or algae, or microbes. Viruses are too small and they do not disperse visible light, but microbes are on the size of the colloidal particles. That means that if we see turbid water, we know that there is something in the water. We cannot say what is in there, but something is in there. How do we measure the particles that are in the water? The turbidity is measured by the amount of light that is dispersed to the side. And this is usually measured in relatively arbitrary units that are related to a standard suspension. And there are a lot of regulations that were usually most of the countries use what is called formazine suspension as standard. In general, if we have more particles, we will have more turbidity. Why do I say in general? Because it depends also in several issues that are related to the particle: the size, the dispersion, the specific form of the particle, if it's like a needle or like a ball or something similar. And it depends also in some chemical properties. For example, if we have soap, so above a certain concentration, the soap will form micelles. But below a certain concentration, those micelles will dissolve. That means that we can suddenly, if we dilute a turbid sample that has soap, suddenly the turbidity will disappear. This will not happen if the particles that contribute to the turbidity are, for example, minerals. We dilute, and then it will be less cloudy, but it will be still cloudy. What about TSS? In TSS, we weigh the amount of particles that do not pass a specific filter. Now, I should mention and emphasize that the parameters are not directly correlated to the health hazard in the water. That means it's not that if you have more suspended solids, the water will be more poisonous or more dangerous, because it depends on the property of the suspended material. The water can be very, very clear, very, very non-turbid with zero suspended solid, but still be very dangerous if there is a soluble toxin in it. That means that we know that there's something in the water, but we cannot say if the water is dangerous or how dangerous the water is. We should remember that what clogs the filters is not the turbidity, but the particles. On the other hand, to determine the turbidity, it's very easy. You can use instruments that measure it online. To determine the suspended solids takes time. You need to filter the water, go to the oven, dry the filter, etc., etc. The process takes at least a few hours. That means that it's very easy to measure turbidity, but the problem is in most cases due to the suspended solids. So the question is, are those two parameters related, and are those two parameters always related? And we have here several studies performed on the ratio between suspended solids and turbidity, measured suspended solids turbidity measured in milligrams per liter, and turbidity measured in what is called nephelometric turbidity units. And we can see that the numbers depend on the type of effluent. For example, in paper industry, we can see that it's more or less 2 to 3. In soap, it's less than 1. In municipal wastewater, it ranges between 2 to 5. But those are generally the numbers that we find when we try to correlate between those two parameters, that we should recall both of them indicate that there are colloids in the water, but they are coming from completely different parts of the science. Turbidity is coming from light dispersion, and TSS is coming from the size of the particles that are in your sample. So if we take a look at a slightly deeper look at a few studies, then we can see here data from Singapore. We can see that there are two cases when the suspended solid is relatively low. That means when the rivers are without any storm, and we can see that when there is no storm, the correlation is quite nice. It's not excellent, but we still have an R-squared of 0.8. On the other hand, when there is a storm and the TSS is higher due to particles, then the numbers are a lot more difficult to correlate between the turbidity and the TSS. Similar results are shown here for effluents that coming from several sources in dry or wet periods. And we can see that, again, there is a slope and there is a correlation, and it looks quite nice. And that means that you can have instruments that you can see when you buy them, that it's written that the instrument measures suspended solids. And this is not the case. The instrument measures turbidity and it correlates it to suspended solids, and this correlation can work quite well if you know what is in your sample, but in such case, you can get relatively limited variability in the ratio between both parameters. But I want to mention a specific case where the correlation collapses completely. We made some study on dairy effluents, and about 6 or 7 years ago, and then we found that in dairy effluents, the ratio between TSS and the turbidity can reach very, very high numbers, 30, 40, and we had one case even with 150. That means that a lot larger than the 1 to 5 that we saw before. The reason in that case was that we had gelatinous polysaccharides that were responsible to very large difference, because they were almost transparent, but they clogged the filters almost completely. That means that when you want to correlate TSS to turbidity, because turbidity is easy to measure and TSS, it clogs the filter, you need to at least at the beginning try to make some preliminary test in order to see if your samples are in the range of most water samples. That means in a ratio of, let's say, 1 to 5, or if it's a very exclusive and unusual sample, like in the case that we found in direct wastewater. And in general, when we're talking about circumstantial relationships, then TSS and turbidity is a very nice case, but there are several of them in water treatment. For example, when we want to know the total dissolved solids, in several cases we measure the electrical conductivity. But we need to recall that we can have dissolved compounds that do not contribute to the electrical conductivity because they are not charged, for example, sugar. Some researchers tend to correlate the absorbance of light at 250 nanometers to phenol. And this is true. Phenol absorbs indeed in about 250 nanometers, but there are a lot of other organic aromatic molecules that absorb up to 150 nanometers. That means that the complete correlation between phenols and light absorbance at 250 can be wrong. I think that the most well-known example is the differences between an element and ion. For example, chloride and perchlorate are both are two anions, but one of them it's a problem for because it's coming from salt, and some plants can be sensitive for it, and we can taste it, but it's not dangerous. Perchlorate, on the other side, it's very dangerous. Another example that I will show in a few minutes is the relationship between zeta potential and the stability of a colloidal suspension. We will talk about it in a few minutes. So I mentioned before that colloidal stability, it's we define a suspension as stable when the particles do not sink. That means the sample remains turbid. But we didn't mention what are the reasons for the particles not to sink. And in general, we have three factors. First of all, we have the size. Very small particles tend to move very slowly due to drag force in the medium. The medium in our case is water, but we also need to remember that, for example, a cloud, it's a stable suspension, even though the particles are water, with a density that is 700 folds larger than the density of the air. That means that the particles remain in place because they move very, very, very slowly, what we call usually stock slope. But there is also some other, two other factors. The charge, in most cases, the colloidal particles in suspension are electrostatical charged. For example, clay minerals usually are negatively charged. Most bacteria and algae are also negatively charged, even though some of them are positively charged. When you take two negative particles and you try to bring them together, they repulse each other, and this avoids its aggregation. That means that the particles remain small. Even if they collide with each other, they do not bind to each other. The third factor, very important in wastewater, is the density. It's also important in stream water, river water, because the density of the particles in water, it's usually more or less the same density as the density of water. For example, algae have more or less the density of the water, and organic compounds in effluents have more or less the density of the water. That means that even if you have a large particle, a non-charged particle, if the density is the same, it will not sink. It will remain like what we call hovering on floating in the water. And it will be very hard to separate it. How do we deal with those very small particles and charged particles? Usually, regular pretreatments are based on two separate stages. As a matter of fact, three stages. The first stage is the neutralization of the charges. Because since we want to obtain larger particles, we need, first of all, to neutralize the charge that causes the repulsion between them. And this is done by what we called in the technical or wastewater or water treatment world, coagulation. After that, we have particles that are neutral, non-charged, but are still very small. Then we add another material, what we call a flocculant. Flocculant, it bridges the non-charged particle and forms larger aggregates, and this leads in the end to flocculation. The particles become larger, and then they start moving faster in our solution, of course, depending on the density. I want to mention that the difference between coagulation and flocculation in wastewater treatment plant, it's clear, it's obvious. Coagulation is the neutralization, flocculation is making the particles larger. But this is not the same in all, let's say, disciplines. For example, I'm coming from the clay minerals discipline, and in clay minerals, if you mention coagulation and flocculation, people will think that you are saying the same, even though that in wastewater treatment, we know that the definition is different. After getting your large particles, then it depends on the density. If the particles have a lower density than water, then will float, and you can divide or separate your clear water by flotation. If those are have a larger density, like minerals, for example, they will sink, and then you can separate by decantation. And if they have more or less the same density of than the water, then you can use filtration to separate them, because the particles are large and are not charged, and then the filtration can be very efficient. That means that we are talking about three different steps that are usually performed in different tanks and different places, and take several minutes to hours in most cases. And that led us to the idea that maybe we can find something that does it faster. But before presenting our, let's say, solution, then let's speak about how do we monitor the treatments in general. In general, in order to monitor the treatments, we do, in most cases, what is called jar test. What is jar test? We get a lot of small vessels with stirrers, and we add several types of coagulants and or flocculants, depending on which stage you are talking about, and you see what happens. That means a real and almost complete trial and error. You don't know what to use, you don't know which coagulant to use. We try until you get a success. Of course, how do you know if you got a success? You measured either the TSS or the turbidity. In most cases, it's easier to see the turbidity, and in several cases, if you have very turbid effluents, then you can see with your eyes if the suspension becomes clearer and how fast it becomes clearer. There is also a possibility of measuring metadata potential. I will mention it in a few seconds. This at least will tell you if your suspension is positive or negatively charged. And if you know if it's positively or negatively charged, you will know which coagulant to use. If it's positively charged, then you will use a negative coagulant, and vice versa. That means that if you have a zeta potential instrument, the trial and error will remain, but it will become easier. We want indeed to know which coagulant. Yes, please.
טוב, מה קורה?
מי שמדבר שם בעברית, שיעשה מיוט. כן, let's go on. If we want we want to know how much coagulant and which coagulant and how much do we need to add. And we also want to evaluate how efficient was our treatment. And this is usually done by trial and error. But I will show you a few different techniques that are more unusual, but can give you faster and more efficient results. Let's start with defining what is zeta potential. If you have a charged particle, then if we remember the double layer model, we know that we have an equilibrium concentration, and near the charged particle, we will have, let's say, ions with the opposite charge. That means if the surface is negative, we have positively charged ions. We have a surplus of ions. Part of them are strongly or relatively strongly bound to the surface, and this is called the Stern potential, and part of them are in what we call the diffuse layer. That means that the distribution of the ions near the particles, and we're talking about tens of nanometers, depends on the ionic strength, but more or less tens of nanometers, the distribution of the ions near the particle is not homogeneous. Now, what we do when we are measuring zeta potential? As a matter of fact, we take our suspension and we put on the sides two electrodes, one positive and one negative. And then we start playing with the voltage between the electrodes. And at a certain voltage, what we get is that the particles are torn away from the surrounding. And this potential, we call it, it's not the Stern potential. It's slightly higher than the Stern potential usually. We call it shear potential or zeta potential. And indeed, it gives us a measurement, first of all, if our particles are negative or positive. And after that, what do we add around the particles? That means that the zeta potential can give us an idea of what do we have in our suspension. And in water treatment, usually we know the kind of rule of thumb about zeta potential and its relationship to how the suspension will behave. If we have a very low, and when I'm saying very low, it can be positive or negative, but very close to zero potential, then it will flocculate very fast and without any problem. If it has values between 10 and 30, then we will have a medium flux, and we will need to add maybe some coagulant. And if it's more than 60, then it will be very difficult to perform coagulation, because our suspension will be very stable. But then again, as in the case of the relationship between turbidity and TSS, this is not always, this doesn't always work. For example, if we take a tap water sample and you put it in a zeta potential measurement, you will get in most cases, a very high zeta potential. In some cases, even larger than 300 millivolts. But of course, the water is very clear, and it clarifies completely with almost zero amount of coagulant. And on the other hand, if we have olive meal wastewater, usually the zeta potential is not so high. It's about 20 millivolts. But in order to make it clearer, you will need a lot of coagulant. Because what happens indeed is that the parameter that it's making the influence, it's not the zeta potential, it's the total charge. Let's take a look at some other example that we all know from chemistry. I will go to that. If we measure the pH and we see that the pH is 1, we know that we have a very acid solution. But we don't know how much base we will need to add in order to make it neutral. If we want to know that, we need the buffer capacity. If we go to physics, even simpler example, the velocity gives an indication about how fast a particle moves. But if a fly that it's flying at 100 kilometers per hour collides with the wall, nothing will happen to the wall. On the other hand, if a truck that it's moving at 5 kilometers per hour collides with the wall will collapse. That means that what we need in order to know how much work is done, it's not the velocity, it's the momentum. The difference between such parameters, it's what we call intensity parameters on one hand and capacity parameters on the other. In this case, we are talking about potential, that is an intensity parameter, and charge, that is a capacity parameter. And if we take a look at winery effluents, for example, and the relationship between the potential and the amount of coagulant that we need to add in order to change the potential, then we see that in winery effluents, the potential changed very fast. And we get almost potential of 0 with less than 1 milliliter per liter of coagulant added. In olive meal wastewater, then we start at only 20 or 30 millivolts, but we need to add a lot of coagulant, more than 7 milliliters per liter, until we get it clearer, because the charge is completely different, even though the potential is small. What's the problem with charge? That it's more problematic to measure it. We need to make a titration. And the titration is made with instruments that are known as particle charge detectors or streaming current detector. And there is a link, if you will get afterwards the presentation, you can get from this link a connection to papers about that. We have a piston that moves, and it moves the particles, and we have two electrodes, and by moving the particles, then a voltage is made between a potential. It's built between the two electrodes, and we measure this potential, and we start adding a titration. But instead of titrating the pH, we are titrating here the charge until we get to 0 charge. That means we can measure the amount of titrant we needed to add in order to get a potential of 0. And if we are able to do that, then we can very easily know how much coagulant we need to add, because we know how many charges we have in our suspension. It's, as a matter of fact, it's a relationship between the volume of the coagulant and the charge of the coagulant to the volume of the effluent and the charge of the effluent. And it's very nice to see that if we increase the amount of coagulant, then you get at the beginning clarification of your suspension. But if you added too much coagulant, then you get that the sample becomes turbid again. And the reason it's obvious. If we have a colloidal suspension, those are charged and they repel each other, so we have a turbid suspension. If we add a low dose, it's not enough. We still get a turbid suspension. If we have the right dose, then we get separation of the particles. In that case, the particles float, mostly because they have air in it, but it doesn't matter. What is important for us is the suspension now is clear. But if you had too much coagulant, then you get what we call an overdose. And in such case, an overdose will lead us to a suspension that becomes stable and turbid again. That means that we need to be in a certain range that yields to you the clarification. It's not like if you add a lot of coagulant, you will get better results. There's the other way around. If you add too many coagulant, in almost all the cases, you will get that the suspension becomes stable again, and you have a turbid effluent. You've spent a lot of money in adding the coagulant, and the suspension is turbid, and you cannot separate your particles. So it's very important to know how much to add, and you can do it in jar test in trial and error, or you can try to measure the charge if you have a suitable instrument, and then test the amounts that are needed. And again, when we want to monitor what's going on, usually we do it by measuring the TSS or measuring the turbidity. There are several instruments that can be more sophisticated, like, for example, a dispersion analyzer that monitors the light that passes through your sample at each moment and each point of your sample. You can see here, this is a centrifuge, and the particles moves to the side due to the centrifugal acceleration, and then you get here the transmission of light. When the sample is clear, then you have almost 90 or 95% light transmission. And that means that if your sample clarifies, you will get high transmissions. If your sample does not clarify, you will get low transmissions. And if I connect between the test tubes that I showed you before and results from such a dispersion analyzer, then we can see that in raw effluents, indeed, the tubes are completely turbid. In those test tubes, we have a partial turbidity, let's say. And the clear samples, we have a light transmission that's not 90%, but it's almost 60%. And in the overdose, we get that the light transmission goes back again to lower values. So until now, I talked about turbidity, suspended solids, how do we measure it, and what we do with that. Let's try to go to our, let's say, invention that tries to deal with the removal of such turbidity and suspended solids in a more efficient way. And you know that we started, as a matter of fact, with very, very low, highly loaded effluents, with winery effluents or olive mills. In such case, if you remember, I mentioned that suspended solids in rivers and springs, if those are relatively clear, can go down to 10 milligrams per liter. In effluents that I'm speaking about, we are talking about several thousands of milligrams per liter. A lot more dense and a lot more charged than suspended domestic effluents. But then again, we wanted to deal with them. We know how to deal with suspended solids. I mentioned before, we use coagulation and flocculation. The problem that is that if you do that with such a highly loaded effluents, it will take a lot of time. You will need two separated tanks, because if you add in the same tank the coagulant and the flocculant, they mix together and you get no coagulation at all and no flocculation at all. And it takes a long time, in most cases hours, and in some cases even days. For example, in piggery effluents in the south of my country, they have a very large tank where they put the effluents for days after adding the coagulant and the flocculant. There's another problem that at the beginning we did not consider, but in the end it happens to be very important. In most cases, coagulants and flocculants are sensitive to the conditions, especially to the pH. And in some cases, you need to do a pre-adjustment and a post-adjustment of pH to a very narrow range. Otherwise, it does not work. And what we were thinking is that maybe we can do it faster and with less, let's say, problems. And the general idea was the following. Since we have a problem with the charge, then let's use polymers to neutralize the charge. That means if we have, in most cases, we will have negatively charged effluents, then let's use positively charged polymers with long chains that can connect to the colloids. We know that we have a problem of size. That means that if we add such chains and connect them to an anchor, a particle in the middle, then when the colloids will connect to our particle, we will get directly a relatively large particle. And if the anchor is made of something that is denser than the water, for example, a clay mineral, then we will get like an anchor, like I mentioned before, that can easily take the particle that we made that is charged, it's non-charged, and it's relatively large, down. And we will get a faster separation, and we'll get a clarification instead in hours, in minutes. In the end, it happened to be that it's also when we use some specific polymers, it's also does not depend on the pH. That means it works very nicely in olive meal wastewater where the pH is 4 or 4.5, and in bromine effluent where the pH is close to 10. Without any pH adaptation, those particles do a very nice work. How nice? You can see here in the movies that are slightly accelerated. Above it's olive meal wastewater, below it's winery effluent, and you can see that we have very nice and very fast clarification. Of course, in olive meal wastewater, it's still turbid and we get a lot of sludge, but after that, we can filter the sludge and get relatively a lot clearer effluent. As a matter of fact, the removal of suspended solids, it's way above 90%, in most cases, more than 95%. In some effluents, we get also very nice COD removal. Depends of the kind of COD that you have. If it's dissolved COD, then it will not remove it so much. That's the case, for example, in winery. If it's particulate COD, like in cowshed effluents, then we can get even 90 or 95% of the COD removed already. But the TSS works very nice in both cases. Now, if we try to measure the particle size distribution and see what's happening here, then in this case, we are dealing with cowshed effluents, and we see that the particles are, part of them, about 20% of them are less than 1 micron, and some of them are more than 1 micron, but less than 2 or 3 microns. Remember that the scale here is logarithmic, and all particles are less than 10 microns and are charged. And if we use our nanocomposites that mentioned before, then we can get flocks that are almost all of them larger than 10 microns and are uncharged, and they sink. They sink relatively fast, but we cannot filter them, because if you have a particle of 20 microns, it's very difficult to use a filter. And if you press on the filter, then you can break the particles, the flocks, and everything will go through the filter again. That means that the general approach here is, as I mentioned before, as I showed before, we add nanocomposites and we get sedimentation and clarification. But if we want to do it faster, even faster, we need larger particles and we need more stable particles. And this is done by adding together nanocomposite and a kind of glue, a bridging polymer. If we do that, then we get very large particles, more than, some of them more than 100 microns. And the general idea is that we start from a colloidal effluent and we add nanocomposite and a glue and a bridging polymer. The nanocomposites bind to the colloidal particles, and the bridging gluing polymer gets together several particles, small particles, and make a lot larger particle. And this is very easily filtered and also sinks very fast. And when I'm speaking of very fast, it's really a question, in most cases, a question of seconds, as you can see here. Again, sorry, I wanted to go this slide. It's not accelerated, it's accelerated velocity. And you can see here we are adding a mixture of nanocomposite and bridging polymer and glue. We are adding them together at the same time, not in separated time. And you can see that it's really a question of seconds. Not always works so nicely, as what mentioned. But then again, in several effluents, we get a very, very fast effect. And in some, when we try to ask for a patent for that, then the patent officer told us, okay, but maybe it's only the glue, only the bridging agent. It's not the case. If we add only bridging agent, then we get large particles sinking, but we get also turbid suspension above it. And if we use only nanocomposite, then we get a very clear suspension, but very small particles. By mixing the nanocomposite with the glue, with the bridging agent, then we get very large particles. How large? This is with an optical microscope. You can see here that when you compare it with the raw effluent and with the nanocomposite alone, we can get, by combining it with the glue, depends, there are several glues that can be used, we can get very, very large particles. So what are the advantages? One of the advantages is that we need only one tank. The time it's a lot shorter. We're talking about seconds to minutes instead of minutes to hours, and it's not pH dependent. Now, what are the problems? Again, like always, there are problems. One of the problems is that we need to be cost effective. Of course, that if the price is too high, nobody will use it. And this is more or less the case, or was more or less the case for several years. Even now, it's used in very specific approaches or cases where when no other solution works. But then again, if we want to use it in potable water, we need to adapt the materials in order to be food grade. And if you want to use it in desalination, we need to adapt the materials to be sure that the membranes are not damaged, because most polymers indeed make clogging or damaging or biofouling to the membranes. And of course, the price. There is another problem that in most cases is not a problem, but or let's say the opposite. In most cases, it is a problem, but not always. We remove very nicely TSS and in some cases even COD, but we do not remove nitrogen or phosphorus. And this is a problem when you are dealing with water, but not always. For example, there is a research group in Migal that works on trying to absorb afterwards the phosphorus in order to use it in circular economy as a fertilizer. That means that they remove everything with our nanocomposites, they get clear water with phosphorus, and then afterwards absorb the phosphorus on a specific solvent, and they separate it and use it as a fertilizer. And they have a really a patent on that in a project that is running in order to show that indeed it really works. So I will end with a few words about if it's possible to apply it in potable water. Again, when we are dealing with potable water, we need to recall that we need to remove algae, and we need at least partly to deal with the pathogens, and we need that the materials, we need them to be food grade, and most of all, yes, we must mention it, it must be cost effective. And at this point, I will show you that we are able to remove algae. We are able to remove at least part of the pathogens. We can use materials that are food grade, but the cost doesn't depend on us. I'm a researcher, I'm a scientist, but the cost, as it is for now, it's not so low. But algae can be removed very nicely, as you can see here. Or here with cyanobacteria from the Lake of Galilee. And pathogens can also be removed. I will show you in another slide that I think is better. Removal of E. coli. And for example, if we are testing the colonies of wastewater, then we get the control in water. If we add only polymer, and all the materials that we use here are in the same amount. That means the nanocomposites have the same amount of polymer that we added as polymer alone. Polymers remove about 75% of the pathogens. That means we have colonies, only 25% of the colonies. If we have clays alone, because nanocomposites are clays and polymers, then we get something very interesting. The pathogens, the E. coli absorbs to the clays, but that means it is removed from the water, but it's still alive. That means the sludge forms very large amounts of colonies. If we add nanocomposites, combination of clays and polymers, then we can get at least 1 or 1.5 order of magnitude of colonies removed. It's not complete, it's not all, but then again, such kind of removal might lower the amount of chlorine used afterwards for sedimentation, for disinfection. So if I go to the summary slide in order to finish it and leave some time for questions, then we can get very nice TSS and turbidity removal in one tank in minutes instead of hours by using clay polymer nanocomposites. And it works in a broad range of pH, and it can be applied in effluents. It can be even applied in current devices, current systems. And in some cases, it will also remove very well the COD. But again, as I mentioned before, it has, of course, its limitation. Thank you very much for your attention, and I will be happy to answer to questions if there are. Sorry. Yes. Any questions? Oh, that's terrible. If there are no questions, it was too good or too bad. But then again, Neta,
Yes, thank you very much, Giora. It was very interesting. I see that no one has questions, so we will finish. So thank you everyone for joining. And thank you again, Giora.
Again, I want to remind you, if you want the slides, then you can send to me an email from the brochure. You get into the link to my website, and then if you send to me an email, I can send you the slides. And we will also, I assume Neta will publish the link to the lecture afterwards.
Yes.
Thank you. Thank you, Neta.
Have a good day. Goodbye.
Bye.